you can compute the accretion rate and things like that as a function of the temperature at infinity. And now, and then we started looking at the complementary problem, which is to look at a gas where the individual gas particle move on bound trajectories around a black hole. And then we found something surprising to us, at least, which is related to this phase-space mixing, which I'm going to try to explain in this talk. So let me highlight that this is work that's with my former PhD student, Paula Rioseco, who is now at Universidad de Chile. And what I'm going to present today is published in these two works. So I'm going to spend some time talking about motivation. So I'm going to present you 4 different systems where you have a damping due to this phase-space mixing phenomena, from plasma physics, stellar dynamics to dark matter halodynamics to plasma around black holes. Then I'm going to quickly, try to define, at least in a loose sense, what mixing is in a general context of statistical ensembles from statistical mechanics. And then I will present results about phase-space mixing in simple Newtonian systems. So 1D problems, starting from 1D problems on a Vlasov gas trapped in a 1D potential, and then rotational symmetric 2 and 3D problems, and then some applications. And the last part of my talk will be about phase-space mixing for bound equatorial orbits around the Kerr black hole, so rotating black hole. So yes, surely is also one of the most fascinating subjects in physics when one hears the statistical physics course or something like this, is the emergence of irreversible macroscopic phenomena from reversible microscopic laws. Okay, and usually where this arises, the typical situation where this arises is when one solves Boltzmann equations, and then one has the H theorem, which is a realization of the second law of thermodynamics. The phenomenon I'm going to describe today is not due to the H theorem. So all the systems I'm going to talk about are collisionless. So it's not driven by the H theorem. So it's a different effect. Okay, which is due to phase-space mixing, which I'm going to explain. And so now to start off, so let's talk about, so let me present a few physical scenarios where this phase-space mixing is known to play or is expected to play a prominent role. So the first system is Lambda damping in plasmas. And this has received, well, a lot of attention recently because of these results by Muo and Villani in 2011. And these systems are simply a gas of electron in a box with Coulomb interaction. Okay, so it's non-relativistic and so on. You can put periodic boundary conditions on the box, for example, and then so the electrons are modeled by the one particle distribution functions, and it solves the Vlasov equation. So P here is the momentum, Q is the charge of the particles, and phi is the electrostatic potential, which satisfies the Poisson equation. So N is the density of the electrons, and then Ni would be the particle density of the ions. Okay, and these equations are completely time reversible. Yet it has been known for a long time that if you look at the observables, so for example, the particle density, then it shows some relaxation process. So for example, the particle density converges in time to has a limit, okay, has a limit. And this has been shown recently rigorously then by in this paper by Muo and Villani. Okay, so even though the equations are completely time reversible, you get a limit. I mean, not only of the particle density, but also of other observables like the kinetic pressure and things like that. Okay, now there's a very similar system, mathematically very similar system, which is if you want to describe a stellar system, for example, a galaxy. So typically a galaxy has of the order of 10 to the 11 stars. So you can model it also as a Vlasov gas. Here the interaction, so the little molecules here are the stars. And the probability that two stars collide is very low. So unless you want to go to cosmological scale, so I mean, if your time scales are just 1 million of years, something like that, then you can safely neglect the collisions between the particles. And then the interaction here is gravitational. So in the Newtonian limit, you get again the same, you have the Vlasov equation, but where now F is the one particle distribution for the stars. And you saw now the Poisson equation, where rho now is the mass density of this configuration. So again, the equations are time reversible, but yet one expects relaxation of the system. So for example, one expects that the density converges, has a limit. Well, as far as I know, this hasn't been proven rigorously, but computer simulations say that show this, and this has been studied for a very long time by astrophysicists. And Lyndon Bell has proposed this mechanism where phase-space mixing also enters to explain why there's a relaxation going on, even though the collisions don't play any roles in the system. Okay, so this is mathematically the same system, just you change the sign here of the interaction. Interestingly, in the proof of Moore and Villani, they also make a comment here. So actually they can change the sign and they still get the same results. So for the result in a box. So here, of course, you don't want to put your system in a box, but otherwise it is similar. Okay, the third system, or the third scenario I want to present is a simulation that some colleagues of mine did recently by Miguel Alcubierre and Darío Núñez and some postdocs and students of them. So what they did, they wanted to get an idea of how a dark matter halo would change in time. So they did a model calculation where they just looked at a Vlasov gas. So again, these are massive particles in an external gravitational potential, which is described by the Navarro-Frank-White potential, which is one of these typical potential that are used to describe dark matter halos. And then what I'm showing here are different snapshots from the simulation. So they start off at initial time. So this is a cut. So this is for fixed angular momentum. So the phase space is basically just R and PR. So this is the radial and the radial momentum. And they start with an initial Gaussian distribution for the distribution function. And then these are snapshots at different times. So then you see this starts moving and then this spiral behavior. But then eventually they see that they note that if they evolve for long enough time, then basically the distribution function doesn't change, and they call it has so it gets to a virialized state, so a stationary state basically. Okay, and also in these systems there are no collisions, so this is again for the collisionless gas. And then what my personal motivation is to understand, say, or eventually what I'm working on is motivated of kind of, if you have an accretion disk, so you have a central supermassive black hole, for example, and then you have some matter around, so it gets accreted, so you have an accretion disk, maybe also jets and things like that. So that's, of course, something that astrophysicists are very interested in modeling nowadays. And then this system, again, you can model it by the Vlasov-Maxwell-Einstein system. So here the electromagnetic fields, especially the magnetic field, is important because you have in the vicinity of the black hole, you cannot do it in a Newtonian way. So here you really need to take into account the general relativistic corrections. So you want to solve the Vlasov-Maxwell-Einstein equations, ideally. So this is the Vlasov equation, the Maxwell equations, and the Einstein equations. So J mu is the current density, T mu the stress energy tensor. Of course, for this system, if you work in the vicinity of the black hole, then the gravity will be completely dominated by the black hole. So you can erase in the first approximation the Einstein equations and just put a background metric like the Kerr metric and solve the Vlasov-Maxwell equation, this background. So there might be a simplification here. Yeah, of course, it's a complicated system, and there are some. So this is an incomplete list of some results, but there has been a local well-posedness result by Mansell, Choquet-Brouillard, and then also some steady-state solution have been found by Andreasen, Eklund-Rhein, and Max Thaler. And there's a small data global existence spherical symmetry. But certainly there's still a lot of work that one needs to do to understand like a system like this. Okay, now let me explain. So in all these systems, so this mixing is expected to play a role. So let me try to explain what mixing is roughly. So for this, we're going to consider an autonomous Hamiltonian system with n degrees of freedom, so n so far is arbitrary, finite, but arbitrary. So we have the 2n dimensional phase space. And then, so the passage from microscopic to macroscopic to a macroscopic description, so this is achieved by computing phase space averages, okay? So if rho t is the ensemble density at some time t, and I have an observable, so a function on the phase space, then I associate it to it this average, which is the integral over the observable over the density. And by Liouville's theorem, so so the rho t, I know what the evolution of the ensemble density is if the system is Hamiltonian, and this is just you can compute it if you know the flow, the phase flow, okay? Okay, now a key question is of course if this system reaches an equilibrium state, okay? And by this, what I mean, if I start with a fairly general ensemble density, then the question is if this average of the observables, so this is the macroscopic quantity that I measure, if this has a limit. Okay, more precisely, I can ask the following question also: does there exist like an equilibrium density, ensemble density, so as a function in the phase space, a density in the phase space, such that this average converges in time to the average measured by this equilibrium density? Okay, and this for all observables in a suitable class, say, no? Which I will do later. I will make this more precise. Okay, so basically, does the system get to an equilibrium? Now note that to answer this question, you cannot simply pass the limit below the integral, okay? Because in general, rho t doesn't have a pointwise limit, so you cannot just pass the limit below the integral and to try to compute this rho infinity and to answer this question. The second observation I want to make is that the phase flow, of course, if this is an autonomous Hamiltonian system, then at least it leaves the constant energy, the surface of constant energy invariant, so they are invariant under the flow. So if this rho infinity exists at all, then it must depend at least on the energy. It must be a function at least of the energy. And now we can define what is chaotic mixing. So what is sometimes called chaotic mixing. So chaotic mixing is if this situation that I described. So if this limit exists, so if there is such an equilibrium ensemble density for observables O, okay, and if this, furthermore, if this equilibrium density depends only on the energy. Okay, and then you can compute this equilibrium density. You can compute it by averaging out the initial distribution function over the energy surfaces. Okay, so it's assumed here that the energy surfaces are compact, etc., so that it is well defined. And this is called chaotic mixing because typically this occurs when the flow is sensitive to the initial conditions, or if the flow is chaotic, so that the information is immediately, I mean, quickly it is spread over the energy surfaces, and then you can replace this this density, this ensemble density, with this averaged ensemble density. And you know that is great because the degrees of freedom is really reduced from 2n to 1. So you start with a system with 2n degrees of freedom, and you end up with rho, which is only a function of the energy. This is actually, this is a condition which is related to ergodicity. It's actually slightly stronger than ergodicity, so you can show that chaotic mixing implies ergodicity. So ergodicity would imply that you take here an time average, but here you don't have the time average, so it's a little bit stronger. And there's a very nice article, an old article by Leibowitz and Oliver Penrose in Physics Today, where they explain all this notion of mixing and ergodicity and so on in an accessible way, accessible at least for physicists. So I recommend this if you haven't seen it. Now, the concept that will be more relevant to what I'm going to talk today is phase space mixing, and this is something that occurs if your Hamiltonian system is integrable. So it is known that the motion is restricted to invariant tori, if they are, I mean, if these invariant spaces are compact at least, and this invariant tori, they are parameterized by the action variables, which I will call J, and then so this system is said to have the mixing properties. So if this condition holds, if this limit holds, and in this case, this rho infinity is a function of this integral of motion. And you can obtain it by averaging the initial density, ensemble density, over each tori. So that gives you a function of the action variables, so energy, angular momentum, etc. So in this case, the number of degrees of freedom is reduced from 2n to n, so it's not that great a reduction, but still, so if your initial density function was a function of p and q, then it ends being a function of j, each half of the variables. All right, so let me give you a very simple illustrative example, a pedagogical example. So if you consider the harmonic oscillator in one dimension, so in one dimension, I mean, here the only conserved quantity is the energy, basically. So chaotic mixing would be the same thing as phase space mixing. So this is the Hamiltonian. You have the symplectic form, and then if I introduce action angle variables, so Q would be the angle variables, and the action variable would be the energy, basically. Then the motion is very simple. Then the motion is just a rotation in phase space, a rigid rotation in phase space. So the equation of motion with Q dot is constant, is a frequency which is 1, and the energy is constant. Okay, so if you started, say, so this is again a phase space, so x and p, and now here there's I draw the level sets of some initial Gaussian distribution function, and if you evolve this according to the Vlasov equation. So each particle just follow the geodesic. I mean, sorry, this equation of motion. So it's just a rigid rotation. So this configuration will be rotating like this, and there's no mixing. In this case, there's no mixing. But now let's suppose I modify the example a little bit. So by requiring that the Hamiltonian now is a function of the energy, a nonlinear function of the energy. So f of E now is E plus a small quadratic or quadratic perturbation. The symplectic form is still the same. So if I play the same game, introduce action angle variables, now the Hamiltonian is a function of E. And the equations of motion is now that q dot is omega, but omega is not constant anymore. So omega would be f prime, which is 1 plus ke. So if k is positive, what happens is basically now this is not a rigid motion anymore, but a differential rotations. And the larger the energy, the faster this rotates. So if I show again snapshots in phase space, so after some time, this initial distribution function will get this shape here. And then if you evolve for more time, it will look like this. And if you evolve for a long time, it will look something like this. And then you see what happens if you wait for a very long time. It will basically fill this like a disk. So it will spread over this region of the phase space. Okay, now let me make this more precise. So try to make this more precise. So let me move on to Newtonian systems in one dimension. So now instead of taking, so now I'm going to take an arbitrary potential, and I'm looking at a simple mechanical system in one dimension in this potential. So the potential is a potential well, an infinite well. For simplification, it has a unique global minimum. And I'm going to consider the Vlasov equation in this for this Hamiltonian. So this is the Newton-Vlasov equation. And now I'm going to do the same thing as before. So I'm going to average or to define what the macroscopic observables are. So I will start by just taking a test function. So something which is C infinity smooth and has compact support on phase space. So phase space here is a potential well cross R. And now I'm computing this average over the distribution function. So I'm going to call this n phi of t. And now I can show, you can show the following theorem. So if f is a unique solution of this collisionless of this transport equation for some given initial data in L1, and now there's a condition. So the condition is that if you look at the period function, so this is the period of the orbit for a given energy. So this should be different from 0 for almost all energy. So in the Lebesgue measure of almost so T of E is a period of the E orbits, and that should be so it cannot be constant on an interval, say. Okay, so if this happens, then you can show that the limits. So the limit of this macroscopic observable that exists, and you can compute it. Not only that, but you can compute it also by replacing f by the average of the initial data over the energy curves. Okay, so there's a limit. Okay, and the proof, actually the idea of the proof, I found it in some paper, some old paper by Lind and Bell of the 62, and it's based on just Fourier methods. So what you do, you write your observable in terms of action angle variables. So capital F is what represents the initial distribution function in terms of action angle variables. Phi is the capital phi is what represents this test function in terms of action angle variables. And then in terms of action angle variables, then the motion is just this differential rotation along the energy curves. So omega would be the frequency associated with each energy curve. And then you do a Fourier, because f and phi are 2p periodic, and in Q, you can represent them by their Fourier series. And you use Parseval's identity, and then you get, you can write it as an infinite sum of this form. And now the argument is that, the hand waving argument is that when you compute the limit when t goes to infinity, if you could pass the limit below the series, then because this frequency is not constant, then you, because of the Riemann-Lebesgue lemma, then basically all these integrals will be damped except the mode with k equal to 0. And the mode belonging to k equal to 0, so f0 here is just the average of f of the distribution function over the energy curve. Okay, so that's the idea of the proof, and then you can make this more precise. So there was a recent paper by Mitchell where the essential arguments are shown, so if you call here I copied again this representation in Fourier space of this observables time t. So if you call this function hk, then you can the hypothesis of the theorem, you can show that hk is a L1 function, and it's the L1 norm is can be summable, and then the part B, you show that indeed this in the limit where t goes to infinity, this goes to 0. So for this, you just need that this function omega of j should not be, its gradient should be, so its derivative should be 0 for almost all j. That's enough to show this. And then you show that this equation star here holds in a strict, not just formal sense. And then you can complete the proof. So those, yeah, simple techniques.
Sorry, Olivier.
Yes.
Where did you use the non-degeneracy assumption on T?
Oh, okay. Yes. So that's essential to ensure that omega is not constant. So no, that is not constant. So I had to use it here. So this omega of j so the gradient should vanish almost nowhere, and omega, so it's to use this Riemann-Lebesgue argument, and omega is basically it's 2p over t, 2 pi over t. Okay, so if this condition is satisfied, that will reflect. That means the derivative of omega with respect to j will be different from 0 also.
Thank you.
So that's essential. If you don't have this, then you are basically in this situation where you can have a rigid motion, and then at least in some part of the space time, and then your observable will be just oscillating in time. So you won't have a limit. Yeah, so this is important. So yeah. All right. So one can extend the theorem a little bit. So this test function doesn't need to be C infinity. So actually it's enough that it's bounded and continuous. But of course, the relevant question is, can you have distributive? Can I generalize this to if phi is a distribution? So for example, interesting macroscopic observables, if you just integrate over p, not over x. So for example, if you look at this this family of observables here, then well, for k equals 0, that would just be the particle density. For k equal 2, for example, that will be kinetic energy density. So these are relevant observables. I mean, the relativistic case, these observables would be like the current density of the stress energy tensor. They have roughly this form here. So now you have a delta distribution here, but it turns out you can still show that the theorem is true if you impose additional regularity on the initial data. So if you ask, for example, that F0 is compact support and continuously differentiable, then you can show, I mean, if you look at the Fourier coefficient of this function phi, then this is a regular function, even though you have a delta here. Once you Fourier transform, if you get a regular function, and you can show that the properties A and C that I mentioned before still hold. Okay, so that's nice. So that's because these are, of course, physically relevant observables. What if you have more than one potential well? Then we certainly don't have a formal result about this, but probably you can do the same thing in each potential well. So you would have to divide the phase space into this differential well, and then you apply the theorem to each well here. So it would be the idea, but I don't have a formal statement to discuss this. Now let's move on to 2 and 3 dimensions. So in the 2D case, and I'm going to restrict myself here to a central potential. So the potential depends only on the radius, not on the angle. And then the system is integrable still. So now you look again at the transport equation, and you have an additional conserved quantity, which is the angular momentum. And then then you can show again that you have the mixing property. So modulo technical assumptions on the potential. So we require some conditions on the potential such that the effective potential, which is basically the physical potential plus the centrifugal term. So that should have a unique potential well for all angular momentum. But if you have this, then you can show again that the mixing property occurs. And the non-degenerate condition that you need here is generalized in the following way. So you should look at what we call the area function. So the area function is if you look at an orbit in the radial phase space, or RPR. So that's the orbit for fixed angular momentum and energy, and A is the area enclosed by this curve. Okay, so this is given by this integral. And now if you looked at the Hessian of this function, then the determinant of this should be 0 for almost all E and L in the admissible range. Okay, so in the one-dimensional case, remember that the period function is just the first derivative of the area function. Okay, and what I require there is that the derivative of the period function, which would be the second derivative of the area function, should be different from 0 for almost all energies. So that's how it's generalized in this case. In 3D, in the 3-dimensional case, again, if you have a central potential, then phase space mixing, as I defined, doesn't hold because there are more than 3 integrals of motions. I mean, you have the energy, and then you have the 3 components of the angular momentum. So the system is, so you have more, this is super integrable. What happens here, you can still show if this, so you can still define the same area function where L will now be the total angular momentum. So you can still show that mixing occurs in 2 of the angle variables. So 2 of the angle variables, they mix, but not the third one. So there's one that propagates that has basically 0 frequency associated to it. And so if you formulate the problem as total energy, total angular momentum, and the azimuthal component of the angular momentum, say you take this as basically your constant integrals of motion, then this angle variables that doesn't mix, that actually turns out it provides the missing information about the angular momentum. So that will give you, if you know the total angular momentum and the azimuthal angular momentum, then you still need to know the orientation of the angular momentum vector in its projection on the XY plane, say. So in this angle is contained in one of the in the angle variable that doesn't mix. Okay, so at the end, in this case, you can show that if this non-degenerate condition holds, the gas will be still the configuration will converge to a configuration that is described by these four integrals of motion. So there are some nice examples which you can find in Bini and Tremaine's book on galactic dynamics. So for example, there's this isochron potential, which is this potential here. So this potential reduces, so this is a parameter B. So it's regular at the center if B is larger than 0. If B goes to 0, then it reduces the Kepler potential. And for this one, you can actually compute this area function explicitly. And it has a part which is the energy, which looks exactly like the Kepler potential. So the period in the radial motion is given by exactly the same expression as the Kepler potential. But then in the angular momentum, it has this more complicated form. So if B goes to 0, you see this is linear in L, and then the Hessian is the degenerates. But if B is larger than 0, then you have the determinant of the Hessian is different from 0, and you have mixing. Okay, there are some other examples, but let me. So the other example is the Navajo Frank-White potential I mentioned before. So that's given by this expression. So it's widely used. And here, okay, we couldn't compute the area function explicitly, but you can still plot the determinants with Mathematica or something like this. And then from this plot, at least from the range which we checked, it seems that this condition is satisfied everywhere. And now this kind of explains, so the last comment I made, so if I go back to this third scenario I mentioned in the introduction, which is a propagation of this dark matter halo. So this explains what they were seeing in the numerical simulation, so that was due to mixing. Actually, we could do a little bit more. So I show you these two phase plots. So on the left is R versus PR. So that's the initial configuration. And these black curves here, these are the curves of constant energy. So this is a one-dimensional problem because the angular momentum was fixed in this simulation. And then Paula, just with a simple Mathematica script, then computed the average of this initial configuration over the energy curves, and that's what you get here. And then if you compare it to this final configuration, that agrees, at least qualitatively, it agrees very well. So it shows what's happening here. We don't get exact quantitative precise agreement, but we think that might be related to the numerical method they're using, because the numerical method that we're using is very good in preserving the number of, the total number of particles, but it has dissipation in it. Okay, so the numerical profile they get here is slightly wider, and the height is a little bit less than we have, but at least at the qualitative level, it seems to be okay. Okay, so let me move to the last part of my talk. So now we want to apply these ideas to the motion of bound bound geodesics, timelike geodesics on Carrick stereo spacetime. So what we have in mind is a gas of massive particles, collisionless, which is propagating around a Kerr black hole. Okay, and to simplify the problem, we started to look at equatorial orbits only, so that we get a two-dimensional system basically. So we look at the Kerr matrix also on the equatorial plane, so induced on the equatorial plane. So the two parameters, the mass and the angular momentum, which we assume is it's a black hole, a soup extremal black hole. Delta is this function r squared minus 2mr plus a squared. And and this integrable because we have free integral of motions that are Hamiltonian, the one particle Hamiltonian, energy and angular momentum of the particles. And then if you look at the motions, also the only non-trivial part is the motion in the radial direction, which is described by this delta squared PR squared is equal of this function R, capital R of R, which is a function, which is a fourth order polynomial whose coefficient depend on the constant of motion E and L. And M is the mass of the particle. So in the case of interest, it has four roots. And so there's one root which is always at R equals 0. Then there's another root which is inside the horizon. And then there are other two, I mean, it depends on the value of E and L, but if you have to have bound trajectories, then you have to have these other two roots, which I call xi1 and xi2, which are the, and you see in this region, R is positive, so this is where you have the motion, and R1 and R2 would just be the turning points. So actually, in this business of parameterizing the bound orbits, it is actually advantageous to parameterize the orbits in terms of the turning points instead of the energy and angular momentum. That makes life a little bit easier. Now, the next thing you can do is to construct action angle variables for this system. So these are these things that have been done in the literature for some time by different people. Well, the nice thing is you can actually compute them almost explicitly. I mean, you can represent these action angle variables in terms of standard elliptic integrals. So the action variables is you can take the energy, the angular momentum, and then J2 would be this more complicated function of so H0, H3, H2, and H1 can be written explicitly in terms of standard elliptic integrals, which I mean I didn't bother to write this here. The angle variables, so they are functions of the integrals of motion and of t, phi, and this angle chi. So this angle chi it parameterizes the R orbits that you have. So this is an angle around these orbits in the RP diagram. Okay, and the phase flow then becomes trivial, and now you can actually so you can re-express the transport equation. So the relativistic transport equation you can write down as this Poisson commutator with the one particle Hamiltonian is equal to 0. And now if you write this in terms of angle variables, then it becomes a simple advection equations, where here you have the fundamental frequencies. So the fundamental frequencies are the derivative of h with respect to j, and normalized by dh by d j0. And then you can formally solve this advection equation. So this would be just a function which, again, is so you have an arbitrary function which is 2 pi periodic in its first two entries, and then you have these fundamental frequencies that appear here, and then the other three variables are just the action variables. Okay, and if you remember Q0, that contains here the time. Okay, so basically this looks formally very similar to what we had in the Newtonian case. So it's just a rotation along these tori's that are defined by J0, J1, J2 with this frequency omega1, omega2. Okay, and now the nice thing, because you can compute this exactly, I mean, you have an exact solution representation, so you can actually do numerical experiments or experiments, so you can compute, for example, explicitly what is the particle density, for example, measured by a static observer. here we took as an example is an observer located in a Schwarzschild background at 6m, and we chose some Gaussian function for f as an example, and then you see, so I plot here the time evolution of the density function. So you see it starts to oscillate as you would expect, but this oscillation is quickly damped. Okay, so n infinity is the asymptotic value of so for t goes to infinity. And this is the same plot, just it's a log plot to see what the decay is. As it seems to decay exponentially fast, but then there's a slower decay, but it has decayed by a substantial factor already. Okay, so this limit seems to exist, and we can actually prove this again by using the techniques I showed you. So by adopting these techniques for the two-dimensional case I showed you before, so again you can compute what the area function is. So it would be this integral, and you can express it again as in terms of standard elliptic integrals, and you can show that mixing takes place if this determinant condition is satisfied almost everywhere. And then, so the thing, so you can compute this determinant by using Mathematica, for example, because the nice thing is that these elliptic functions, they are tabulated, they are known in this Maple or Mathematica libraries. So then you can just plot what the determinant is and check it if it is 0 or not. And here, what I'm showing you is a plot, is this determinant condition basically as a function of, so instead of using E and L, you use R1 or R2, or you can introduce like a semi-latus rectum type variables P and eccentricity type variables E. So if that would be the Keplerian motion, that would be exactly the semi-latus rectum and eccentricity, but you can still reparameterize R1 and R2 by P and E. And in this diagram, so what is below this diagonal line, that would be the admissible phase space. And you see now that, so what you find is that this determinant condition is satisfied everywhere except at points on this blue curve here. Okay, now if you believe that's really true, then if you combine this with the theorem that we showed before, that it's enough that this determinant condition is satisfied almost everywhere, then you have the mixing property in this equatorial plane of the Kerr black hole. So it's still, we haven't found this what these points on this curve represent, what kind of orbits they represent, if they are what is special about these orbits. So I mean, people have studied what are like orbits with resonances and things like that, but that doesn't seem to. It seems to be something that hasn't been studied before. At least we haven't found anything in the literature where about this blue curve. So the mixing seems to be slower near those points, but still mixing occurs. Okay, so that's my last slide. So let me end. So what we are working on now, or what we want to do, say, is to generalize these results for bound trajectories on the Kerr spacetime, relaxing the condition about the equatorial plane. So and the conjecture then would be that along the world line of a station observer, the observables such as stress energy tensor or the particle density or things like that associated with a collisionless gas converge to those belong to an average distribution function, which is due to phase space mixing. So so in 3 dimensions, so the nice thing about Kerr is that it also forms an integrable Hamiltonian system in the full 3D case. I mean, you have the Carter constant in this case, so you can still separate the motion into radial and polar motion. So you can still use these old-fashioned techniques I'm using here to analyze the problem in principle, and then so the conjecture, or what we are trying to show, say, is that you still have phase-space mixing in this case. So basically what would happen is that the distribution function then, which initially is a function of 6 variables, will be reduced to a function of only 3 variables, which are energy, angular momentum, and the Carter constant in this case. If true, that would be very nice, because in particular, this equilibrium distribution function, you can show it is automatically stationary and axisymmetric. So with this, you would show that the end state is stationary and axisymmetric. So somehow everything that is not axisymmetric, for example, will go away or averaged out. A few comments. So these results that we have obtained is compatible with what is known in the literature, in the astrophysics literature at least, by the strong genes theorem, which is also due to Lind and Bell, which states that in an integral Hamiltonian system, the steady state should only depend on isolating integrals of motion. So the isolating integrals of motion here would be exactly the action variables in this case. As I said, so this conjecture has been shown for the restricted case of equatorial orbits, and the problem, so as I mentioned, is reduced from 6 to 3 dimensions. So if you want to study steady state, say, that arise as an end state of this mixing phenomena, you don't need to put a lot of, so you can look at distribution functions, say that it is safe to look at distribution functions that depend only on the integrals of motion. And in the case of the equatorial plane, the reduction is from 4 to 2. There are still open questions, of course, that we are interested in. So the one question that seems to be difficult to answer is what is the associated time scale? So how fast does this converge? So that seems to depend on several aspects. So for once, on the smoothness of this distribution function, because the Riemann-Lebesgue lemma basically tells you how fast this converges, depends on the smoothness properties of the distribution function, but it also depends on how well or how close you are on violating this determinant condition, things like that. Still, in the few numerical experiments we have done on a Schwarzschild background, we have seen that typically these are quite fast. So in this, so there seems to be a few thousand crossing times, which even for a supermassive black hole is I mean, for an astrophysical timescale, this is quite quick. Okay. And then of course there are other things we're interested in, like characterizing or understanding what are these final states or how you can build them. And it would be great, of course, to look at perturbations of the system. So adding the self-gravity at the perturbative, in a perturbative form, or add an electromagnetic field or collision perturbatively. So there are many things one can do from here. Okay, so let me stop here. Thank you very much for your attention.
Many thanks, Olivier, for your talk. Is there any questions and comments from the audience for Olivier, from the people working on steady states, for instance?
Hello, Olivier.
Hello, Jacques.
I wanted to ask you, so if I consider, let's say, a Schwarzschild or curve, and I construct the action angle variables that you consider, the change of coordinates from the regular, basic, I don't know, R, T, and these canonical momentum variables to the actual angle variables, is it completely smooth? In particular, as you are leaving the domain where you have bound states, I'm thinking at the transition between bound state and non-bound states.
Right. No, it is not. So actually, you have to take away. So first of all, I'm concentrating on bound trajectories, and you also have to remove some zero measure sets, like for example, circular orbits. The circular orbits, these variables, they degenerate. So you have to take them out when you do the analysis. But since it's only a set of measure 0, then you can still show that the results go through as long as you stay in this region of bounded trajectories. So if you want to consider also unbounded trajectories, so I think what you would have to do is divide your phase space into 2 regions, the one corresponding to the bound trajectories, another one corresponding to unbound trajectories. And then, yeah, so that might be problematic if you want to study what happens just at the threshold between the two, then probably you would have to do something different, right? But at least if you you can do this separation.
Thanks, Olivier.
Yes.
Further questions or comments? No? Then
I have a quick question. I just want to wait, didn't want to interrupt someone else. Okay. So, well, this is a very nice material. I really appreciate this. So maybe the question is, I hope the question is appropriate. But so this relies, of course, heavily that you really understand the geometry well, as you lined out in detail. Yeah. So would it be so like this final aim that you display here, that the gas would then go to some stationary axisymmetric solution, for instance, so you have some good guess for the final state. Would it be, do you have any idea to achieve this with a bit more robust method that would be able to incorporate eventually back reactions and so on, like on a more classical PDE approach? Do you have any idea?
Yeah, that would be very nice. I have no idea, but I think Jacques told me actually a year ago that I think you have some ideas, some better ideas than I have how to do that. So I think it would be really, really nice if one could move away from these old-fashioned methods and use this, how you say, the more robust methods. Still, I think this issue about the determinant condition, and somehow I think they should pop up, because this is like, I mean, if this determinant condition would be violated on a set of which is not of measure 0, then you would be dead, right? And then you wouldn't have mixing. So these things you eventually will have to need to understand anyway. So yeah, but I think that would be, that's a really nice, a really great question, and it would be really, really nice if one could do something with more modern methods. Yes.
Okay, great. Thanks a lot.